Well, hello, everyone.
Hello.
Excuse me.
So just to let you know, Dr. Musk, I'm here, but I'm kind of half not here. I'm in another science training at the same time, but I'll be paying attention to both until 5:30.
We're going over shapes and polarity and intermolecular forces today. Actually, I think just shapes and polarity, and then the intermolecular forces doesn't come until chapter 8. So shape and polarity, that's our big jobs today, and reviewing how to do Lewis structures in the first place. So our video from last Thursday, we learned Dr. Musk's quick rules for drawing good Lewis structures. If you weren't there for that recitation and you haven't watched the video, which the video didn't actually post until today, that's my bad, totally my bad. I'm going to give you the 3 rules, and then we're going to do some examples to be sure that you know how to apply them. So those are the shortened version of the rules from last video. We're going to add up all the electrons in our formula. Remember, whatever number of all valence electrons in our formula, whatever number that is the exact number of electrons that our Lewis structure has to contain. It can't contain more or less. Then we're going to draw a skeleton structure. So that's the bare bones showing just the minimum number of covalent bonds to hold that molecule together. And then we're going to use that as our scaffold to fill in the remaining electrons around. All right, so let's give it a shot for something that we haven't done yet. Let's try. Let's try SO2. So when we go through the steps for SO2, here's how that looks. First, I'm going to total up the number of valence electrons in this formula. When I look at sulfur, it's a group 6 element, so it has 6 valence electrons. When I look at oxygen, it's also in group 6, so it has 6 valence electrons. So a sulfur with 6 valence electrons and then 2 oxygens with a total of 12 more valence electrons gives us 18 total valence electrons in this formula. So what that means is that our final Lewis structure should have exactly 18 electrons in it. It can't have more or less than that. Then we're going to draw a skeleton structure, step 2. So generally speaking, for small Lewis structures, whatever atom is listed first is the central atom, the one that's in the middle, unless the first atom listed is hydrogen, because hydrogen can never be in the middle because it only ever forms one bond. Okay, so we're through the first 2 steps. That's pretty quick. Third step, we have to fill in the remaining electrons to give all the atoms in the structure an octet, 8 electrons. So that's our octet rule. We learned about one exception to that octet rule last time, and that's boron. So boron prefers, for reasons that we don't have to get into in this class, to have 6 electrons around it instead of 8. All right. Most elements prefer 8 around them. There are some exceptions. For example, sulfur once in a while goes crazy and ends up with 12 electrons around it instead of 8. That's an exception to the octet rule also, but not one that I expect you guys to remember for this class. So boron is the exception that I want you to remember, just so you remember that there are exceptions. Okay, we've used 2 4 electrons creating that skeleton structure. Remember that a covalent bond we represent as a dash, that represents a pair of electrons that's being shared between those 2 atoms. So we have 14 electrons left to put into this structure in order to give all 3 of those atoms an octet, a total of 8 electrons. So let's start assigning electron pairs to give all the atoms an octet. 2, 4, 6, 8, 10, 12. Uh-oh. If we look right now, I'm counting a total of 2, 4, 6, 8 electrons around oxygen on the left, a total of 2, 4, 6 electrons around sulfur in the middle, and a total of 2, 4, 6 electrons around oxygen on the right. I only have 2 more electrons to put into this structure. I've used 16, I only have 2 more. And right now, this sulfur is short 1 pair of electrons from having an octet. This oxygen is also short a pair of electrons of having an octet. The only way for us to correctly do number 3 for our list here is to make the last pair of electrons another shared pair of electrons, because then it will belong to both of these atoms instead of just one. Trista, are you comfortable with that? You look like you're digging it.
Yeah, I just had a question. Does it matter which oxygen has the double bond?
No. So actually, that's a very intuitive question, because today we're going to be talking about examples just like this. So
Okay.
is it any less valid if I chose to share an extra pair of electrons with the oxygen on the left instead? No less valid at all. All right. They are equivalent structures. Now that actually means something really special about this molecule. It's something that I wanted to mention today as part of our discussion. So the thing that I want to mention today is what happens when we have more than one Lewis structure that fulfills all of these rules. All right. If there are multiple structures that we can draw just by moving the electrons around and they fulfill the octet rule both ways, then the reality is that neither one of these structures is a perfectly accurate representation of what's going on with SO2. So what we see in SO2 in our Lewis structure is a little bit of a lie, and we have to sort of diagnose that. All right. So how is it a lie, and what is the real truth? The real truth is, even though our picture shows a double bond and a single bond, in SO2, there aren't any sulfur oxygen double bonds, and there aren't any sulfur oxygen single bonds. The reason why is because even though neither of these 2 structures that we drew to represent SO2 is the full truth is like the average in between them. All right. So the rules of Lewis structures make us assign each pair of electrons to just one place. But in some Lewis structures, and this is an example of them, a pair or sometimes multiple pairs of electrons can exist in more than one place. They're being shared over multiple bond locations. So experimentally, the way that we figure this out is we take a look with our tools that allow us to diagnose what the length of that bond is and what the length of that double bond is, all right, or what we think is a double bond. Chemists know from experience that single bonds between two atoms are always longer than double bonds are. Double bonds are longer than triple bonds. So based on bond length, we can tell what kind of bond we're dealing with. And when we look at the bond lengths in SO2, when we use our tools to diagnose that, instead of seeing one shorter sulfur oxygen bond and one longer sulfur oxygen bond, the reality is that both of these bonds are exactly the same length as one another. So what does that tell us? It tells us that if they're the same length, they have to be exactly the same kind of bond as one another. Those two bonds, even though they don't show it in our Lewis structure, they're identical to one another. So what does that mean? If they're an average between what the bond looks like in this structure and what the bond looks like in this structure, then in reality, we have a total of 3 covalent bonds that are being averaged over 1, 2 bonding locations. So each of the places where a sulfur oxygen bond exists of some type, I call those two things bonding locations. So we have a total of 3 bonds that are averaged over 2 bonding locations. So each of those bonds is a 3/2 bond, a 1.5 bond between sulfur and oxygen. So that phenomenon where a pair of electrons, so if you're thinking about how the electrons are being shared here, imagine that there's a single bond here and a single bond here all the time. And that last bond is actually being shared over both of those bond locations at once. So anytime we have a pair of electrons that's being shared over multiple bonding locations, we call that phenomenon resonance. So resonance actually makes molecules a lot more stable the more electrons that they have being shared over multiple bonding locations at once. And just so that we're clear, that doesn't mean that that bond is either on the right or on the left at any given time. So it's not like that pair of electrons flips back and forth really quickly. That pair of electrons exists in both of those places at once. All right. Now I can't do that. I can't be downstairs watching television with my wife, which sounds kind of cool to me right now, and also teaching at the same time. But electrons are really small and really fast, and they don't have to abide by the same rules that I do. So an electron pair can be located in multiple places at the same time, which is why our Lewis structures, because we're forced to draw them with an electron pair existing in only one spot, our Lewis structure model sometimes falls short when we have Lewis structures where a pair or more pairs of electrons can exist in multiple bond locations at the same time. That's the phenomenon called resonance. So let's take a look at another example of a molecule that has resonance. The carbonate ion, CO3 2-. So see if you can draw me a good looking Lewis structure for carbonate. Dustin, is this making some sense?
Yeah.
Good. Okay.
Yeah.
I mean, you don't have to have your camera on, but I can't, with the the black screen of death, I can't tell if you're like digging it or if you're totally confused. So just let me know if you need more explanation. I'm happy to stop, okay?
Yeah, will do. I'm following along so far.
Good. So hopefully in step one, you diagnosed that there were a total of 24 valence electrons in that formula. Have to have exactly that many in our Lewis structure. There's our skeleton structure. We know we have to have at least one bond from carbon to each of those three oxygens. Again, our first atom listed is normally the central atom of the Lewis structure. So we've used 6 electrons. We have 18 left over to give everybody a full outer shell of electrons. So that's 8 an octet. So I have put in 16 electrons more into my structure now. I only have 2 electrons left to put into my structure. And right now that carbon only has 6, that oxygen only has 6. The only way that we're going to be able to give a full outer shell to both of those, to give an octet to both of those, is to share another pair of electrons. So that is a good looking Lewis structure for carbonate. However, that is an equally good looking Lewis structure for carbonate, sharing that extra pair of electrons with this oxygen instead of that one. That is also an equally good looking Lewis structure for carbonate. All 3 of those equally represent carbonate well, which means in reality, none of them represent carbonate very well individually. The reality is that if we have multiple Lewis structures that we can use to represent a molecule, the truth is an average of those Lewis structures. So how do we figure out what those bonds between carbon and oxygen actually are in carbonate? First of all, they're not single and double bonds. All of the bonds between carbon and oxygen in carbonate are identical to one another, all right? But what are they if they're not single bonds or double bonds? Well, in any one of those Lewis structures for carbonate, we have a total of 4 covalent bonds being shared between carbon and oxygen. So 1, 2, 3, 4 covalent bonds being shared. And they're being shared average over 3 bonding locations. So those carbon-oxygen bonds in carbonate are all 4/3 bonds. They are 1 1/3 bonds. Another way of thinking about that is Each one of those locations has a full pair of electrons being shared there, but the last pair of electrons is being shared over all three of those bonding locations at once. So each one of them gets a third of a pair of electrons. So I guarantee you resonance will come up on exam 2, and when it does, hopefully you can explain what that means. So resonance, the way I like to define it, is that electrons are being shared over multiple bonding locations. All right. And as a result of that, we get these weird things that happen, like we can have fractional bonds. All right. And if we really think about it hard, which is like beyond what we want to do for this class, it also means that we can sometimes have fractional charges on atoms. But we're not going to talk about that because it's just a little too much like stomach churn for this class. Okay, so we've done a little bit of review with the rules of writing good Lewis structures. We've talked about something extra for Lewis structures that can have more than one arrangement of electrons that represents that structure. We call that resonance, and we've talked about what that means. And there are a couple more things that we have to discuss when we're talking about Lewis structures. So when we talk about a Lewis structure, each atom that is bound to more than one atom in that Lewis structure has a characteristic shape. All right. It's really important for us to be able to predict what that three-dimensional shape around that atom is, because shape, the three-dimensional shape in covalent compounds, is super important for how they fit next to one another and how they do their bonding. So us figuring out what they look like in 3 dimensions is a really important part of understanding how to draw and interpret Lewis structures. All right. So that being said, what I would like you guys to do is draw me your best possible Lewis structure for each one of these example problems. And then we'll talk through the theory that allows us to predict the shapes. So it's going to be like a double good whammy in that we get a lot of practice drawing Lewis structures, and we also get to use those as models to talk about shape. All right. So let's do HCN. And 3. And BF3. Remember that boron's an exception to the octet rule, so this one's going to look a little weird. All right, it only have 3 bonds to boron. We'll just recycle SO2. All right, that's an important one because it has a different shape. We looked at this one together last time, but remind yourself how to draw that Lewis structure. That's formaldehyde. Okay, that list should be enough for us to discuss all the shapes around central atoms that we have to worry about for this class. So draw me good Lewis structures for all those. I know that'll take a little time, but that's cool. We're practicing Lewis structures. That's a good use of time. So I'm going to fill them in little by little. There's my first HCN. So I threw the first few into the chat, onto the page. If you guys will let me know when you're finished working on these, since there are only a couple of people in anyway.
I'm done.
What about you, Dustin? You need another minute? Don't feel bad if you do.
Yeah, I'm still working on the last two.
Okay, just let me know when you're done.
Will do. All right, I'm done.
Sweet. Let's compare answers. You guys get the same thing I did for those?
Yes.
Good.
Yep.
Good. So what can these structures teach us about the shapes of the central atom? All right. So what we're worried about is how the other things are arranged around the central atom. So when I talk about the shape, I'm talking about the shape just of one central atom in a Lewis structure. Okay. And we're going to start with the easiest one, which is HCN. So in order to talk about shape, we use this theory with a cool acronym called VSEPR theory, except it's spelled VSEPR. So VSEPR theory is the theory that allows us to predict the shape around an atom in a Lewis structure. So that stands for valence shell electron pair repulsion theory. Now, that sounds really, really hard. Valence shell electron pair repulsion. That sounds like something out of Star Trek, except it's not. It's really easy. So all that big acronym means, valence shell electron pair repulsion, is that electrons repel other electrons. So electrons want to be as far apart from other electrons as they possibly can be. And that includes when we have electrons that are surrounding a central atom. So what we define in order to figure out how far those electrons can be from one another is something called a number of electron groups. So an electron group can be a single bond, or a double bond, or a triple bond, or an unshared pair of electrons. We often refer to those as lone pairs. So any one of those counts as one place around a central atom where there are electrons. So we call those electron groups. And the reason why it's important for us to define how many electron groups is, it tells us where those electron groups are likely to go outside of being or around that central atom. So the reason why HCN is so easy as our first example is because when we look at HCN, remember, a single bond counts as one electron group. A triple bond counts as one electron group. So there are only 2 electron groups around that carbon in HCN. And the reason it's really easy is, how hard is it for us to figure out where those 2 electron groups are going to be if they want to be as far apart from one another as possible? So where would they go? On opposite sides, right? On opposite sides of that carbon. So what's the farthest apart those can be? We often define the distance between 2 sets of bonds with an angle. We call it a bond angle. So the bond angle from that single bond over to that triple bond is going to be what? If they're as far apart as they possibly can be from one another.
180 degrees.
You got it, 180 degrees. So that bond angle is what lends us a name for this kind of shape. Because in this shape, there are only 2 bond groups, or sorry, there are only 2 electron groups. They're 180 degrees apart from one another, which means that all 3 of these atoms exist right in a straight line with one another. All 3 of these atoms exist in a perfect straight line with one another. So we call that shape around carbon linear. All right. Now, you'll understand why I picked the molecules that I did, because we just did something with 2 electron groups. The next few examples that we're going to look at are all going to have 3 electron groups around the central atom. So BF3 looks like this, 3 electron groups around that central atom. And formaldehyde looked like this, also 3 electron groups around that central atom. And SO2 also had 3 electron groups around that central atom. Remember that a single bond can count as an electron group, or a double bond, or an unshared pair of electrons. So this is the first place where we're going to get to an example where the Lewis structure, the way I've drawn it, it's a correct Lewis structure, but Lewis structures don't directly indicate what the shape is around a central atom. So we know that this bond angle, even though I've drawn it as 180 degrees, It can't be 180 degrees. And the reason why is there are 3 electron groups here. So with 3 electron groups, what would our bond angle look like? The farthest apart that any of those 2 bonds could be from one another if they're evenly spaced out. So you got to do your geometry a little bit. How many degrees all the way around the circle? 360 degrees, right? And then to go from the top of the circle down to that next bond, you're going 1/3 of the way around the circle. So how many degrees do you think it is? The bond angle from here to here?
90 degrees.
Not quite. That's if we're cutting our circle into quarters.
Okay.
So we're cutting it into thirds, right? So 360 divided by 3 is 120. 120 degrees. Now, same thing here. Even though that is a double bond and that's a single bond, now in reality, there are small differences in the bond angles here because that carbon-oxygen double bond takes up a lot more space than that teeny little single bond to hydrogen. So this bond angle is probably going to be a little bit bigger than this bond angle between the 2 hydrogens. We don't have to worry about those little quibbles in this class. If we just remember that thing has 3 electron groups, I know all my bond angles in there are going to be about 120 degrees. That's plenty close enough for me. All right. Now also here, 3 electron groups around that central atom. Even though I've drawn all 3 of these in a straight line, they're not in a straight line. The bond angle here is actually 120 degrees. So when I draw SO2, and I'm being careful, I actually draw it where the bond angle approximates what I know that shape is going to be like. It's going to look like this because there are 1, 2, 3 electron groups around that central sulfur. So our bond angle between that, or between those bonds, is going to be about 120 degrees. So does that mean that it was wrong for me to draw this Lewis structure this way? No, it's fine because Lewis structures don't directly indicate the shape around a central atom. The number of electron groups around that atom is what dictates the shape. All right. So what name do we give to these shapes? In this case and in this case, the name is the same because we have 3 different atoms bound to that central atom, which means that all 4 of these atoms are in the same XY plane. All right, they're all in the same plane as the paper, and that plane forms the shape of a triangle. So the name that we give to this molecule and this molecule, the central atom anyway, that boron and that carbon, those shapes we call trigonal planar. So trigonal meaning like a triangle, and planar, all the atoms are in the same plane. Just to let the cat out of the bag a little bit, Jennifer has a really awesome study sheet that has this information also, so you'll definitely want to grab that and use it as a study tool, because it's like a nice table that you can refer back to when you get a new molecule that you haven't seen before, and just look and see, well, how many electron groups does it have? Are there any of them that are lone pairs? In that case, it's got to be this shape. So for a lot of people, that study aid is really, really useful. Now, there's a different shape when we're looking at SO2. The reason why is one of our electron groups, one of our 3 electron groups here is a lone pair, which means that we don't have anything up here to be able to complete our triangle, all right? So we can't call this trigonal planar anymore because there's no 3rd atom to form the triangle, all right? Now, it does sort of look triangular, but in this case, what we're going to focus on is now we have only 3 atoms in that structure, but the bond angle between the atoms on the outside is different than it was when we had 3 atoms that were all in a straight line and called it linear. So we can't call this linear anymore because the bond angle is 120 degrees instead of 180. So if we can't call this linear with those 3 atoms because it's not in a straight line, instead we refer to this shape as bent. Now, I really like teaching these shapes, and I also really dig the shapes themselves. And the reason why is because if you look very carefully at that shape around the central atom, lots of times the name refers directly to what it really looks like. To me, that looks bent, right? It's not in a straight line. For HCN, all 3 of those atoms were in a straight line. It looks linear. Trigonal planar, if you pay attention to your roots here, all the atoms are in the same plane. Plane is in the shape of a triangle. So the names always refer to what the shape actually looks like, which is awesome. Some of the names refer to shapes that are a little harder to see. So we're not going to talk about it in this class, but if we had something with 5 electron groups around the central atom, I'll show you in a second, all right? Total enrichment, but for now, we'll do the rest of the shapes that we actually have to learn instead of ones that we don't for this class. Okay, so we've done the 2 different shapes that we can end up with for things with 3 electron groups. We can either have trigonal planar, or if one of those 3 electron groups is a lone pair, we get bent instead. Now, it gets harder when we get to things with 4 electron groups. This is something that takes a lot of practice to visualize, which is why the lab that we are doing this week and next week is a lab where you guys are going to be drawing Lewis structures and actually using a computer program to look at 3-dimensional models of those structures after you draw them. All right, that's a really useful way to start to see what those shapes look like in 3 dimensions, is to have a computer simulation. When we do this together in person, we actually build the models from the model kit, so you can hold them and turn them around and look at them. But the computer work it's pretty good also. You can still rotate them in 3 dimensions, like lots of the same things that we could do in class together. You can do with those, and some things we couldn't do in class together, like measuring bond angles from actual experimental data. It's hard for us with a ruler to reach in and measure an exact bond angle between 2 chemical bonds. They're pretty tiny, right? But the computer simulations can tell us that information. So there's really cool stuff in the lab coming up for this week. Now, Trista, if you thought that we have 4 electron groups here, if all of them were in the same plane as the paper, then going a quarter of the way around the circle here is where we would expect that bond angle to be 90 degrees, right? But it's not. It's not. And the reason why it's not is because all 4 of these electron groups can get farther apart from one another than 90 degrees if we think 3-dimensionally instead of just in the XY. So what's going to happen is we're going to have 2 of those hydrogens bound to carbon in the plane of our paper here. But one of those hydrogens down here is now going to be coming out at us. And I'm going to draw that by wedging my bond, all right? So that wedge means something that's like pushing out towards you in 3 dimensions. Hey, I can even do that on the camera, right? So that's what that hydrogen is doing. It is like creeping out at you. And the last hydrogen that we have is going to be going back into the paper. We represent that with dashes. So the farthest apart that 4 electron groups can be from one another, and Miss Jennifer built a model for us down there to look at. Do you want to rotate that around for us? Ooh. I love how much forced perspective there is with the camera. The atoms look so much smaller on the back side than they do on the front, even though all of them are the same size. That's really neat. So when we have 4 electron groups around a central atom, you should memorize this bond angle because it's not one that you would like automatically think of like 90 degrees or 120 degrees. It turns out that the bond angle when we have 4 electron groups around a central atom ends up being the very nice round number of 109.5 degrees. At some point, I saw a geometric proof of that bond angle. Like basically, if you have rays pointing out from a point mass and they are as far apart from one another as possible, what is the angle between two of the rays? You can derive that with pure geometry, and it's 109.5 degrees, and it's not an easy geometric proof at all. All right. So anyway, I kind of like geek out on geometry proofs sometimes, but that one was like after I was already old enough that I didn't care about them as much anymore. So I was less enthused about math than I was back in college when I was a math minor. And I thought, wow, that would have been really interesting to me like 8 years ago. And now, okay, it's 109.5 degrees. So what do we call this shape? You have to use your imagination and think about it in 3 dimensions, all right? If we think about this in 3 dimensions and imagine that those 3 hydrogens form one side of a 3-dimensional figure, and these 3 hydrogens form another side of a 3-dimensional figure, and this hydrogen and this hydrogen and this hydrogen form another side, the back side of a 3-dimensional figure, and then this hydrogen and this hydrogen and this hydrogen form a 4th side on the bottom. What we end up with is a 4-sided figure where all 4 of the sides are exactly the same size. And the geometric name for that shape, that 3-dimensional shape, is a tetrahedron. So that is why we named this shape tetrahedral. What if we take one of our bonds away and replace it with an unshared pair of electrons? Well, that's exactly what we did when we drew the Lewis structure for NBr3. So we know that there are still 4 electron groups around that nitrogen in NBr3, which means that our shape is going to look a lot like this, except one of those 4 electron groups is going to be replaced by just a lone pair stuck to that nitrogen. So if I was drawing what I expected NBr3 to look like in 3 dimensions, I would draw it like this. I'm not going to draw all the lone pairs in around the bromines because we don't care about that anyway. All we care about is what's the shape around nitrogen. So that is what NBr3 looks like in 3 dimensions. Jennifer built a model that actually has nitrogen. So when we build models, and on the computer as well, you'll see this. The classic color that we use for nitrogen is like a baby blue color. Carbon's normally black, hydrogen is white, halogens tend to be green in those model kits, sulfur's yellow, oxygen's red. So anyway, that's something to learn as you go. But when you're building those, you'll notice that certain atoms always have the same colors in the model kits. And it's really frustrating because if you have a model kit that is like more than 20 years old, carbon used to be gray instead of black. So it's like irritating. And some of the cheap model kits have hydrogens that are kind of a gray shade instead of white. So you're like, what is that? Is that a carbon or I don't get it. Like, so anyway, it's important to know your own model kit when you build those models so you know what kind of atoms you're talking about. Now, how do we name this shape? We can't call it tetrahedral anymore because our 3-dimensional figure does not have 4 sides that are all the same size anymore. All right, the bottom is actually wider than the other sides are. So we name this because it sort of looks like a 3-sided pyramid where nitrogen is at the apex of the pyramid. So a 3-sided pyramid, we give this the name trigonal pyramid. That's the name of our shape. Whenever we have a central atom with 4 electron groups, where 1 out of the 4 electron groups is a lone pair. It's always going to be trigonal pyramid. Now, some books will actually turn this into an adjective instead of the noun form and call it trigonal pyramidal. Like, wow, that is really trigonal pyramidal shape. And it just makes me chuckle to even say that. So I just use the noun form instead. The shape is trigonal pyramid. But if you like trigonal pyramidal, then that's a perfectly valid name for that shape as well, if you want to use the adjective form. All right, it just makes me giggle, and I can't stop giggling when I say it too much, so I avoid that because it's unprofessional. And then finally, water. So oxygen is our central atom. Now, what I'm going to do here is I'm going to take advantage of the fact that I could put those 2 lone pairs on oxygen in the places where our 2 groups that are coming out at us and going back into the board would be. So that leaves us with a hydrogen pointing up this way and a hydrogen pointing out that way and a bond angle here of somewhere close to 109.5. All right, our bond angle's here also close to 109.5. Not exactly, but close to 109.5. So what do we call this shape? We can't call it tetrahedral because it's not a 4-sided figure where all the sides are identical anymore. We can't call it trigonal pyramid because there's no pyramid any place anymore. All we have is 3 atoms left now. So the way we name this is the same way we name something with 3 atoms up here. These 3 atoms are not in a straight line. So we call this shape bent. So that's something that troubles students sometimes. How can you have 2 different shapes that are both bent? Well, this is just a little bit more bent than this is. They're both bent. This one just has a tighter bond angle. All right. We can call both of them bent though, and that's the correct terminology. So those shapes, anything up to 4 electron groups around a central atom, you will be responsible for being able to diagnose if a central atom is one of those shapes. All right, you should be able to tell me what the shape is of any central atom with 4 or less electron groups. So that being said, let me show you a really cool example of a molecule that violates the octet rule and ends up with 5 electron groups instead of 4. This is total enrichment. You do not have to know this for the test. If I look at the Lewis structure SF4, this ends up being the best Lewis structure to represent it. We are not going to worry about bond angles in this, all right? But what I do want to do is I want to show you the 3-dimensional shape of SF4. Let's see if I can find it in an easy place to look here. So just a quick reminder, we have talked about how to name covalent molecules. How would I name SF4, that formula? So if I didn't know how to search for it, how would I name SF4? What would I call that? Remember covalent compounds? We have to talk about how many of each kind of atom there are in that formula. So we have 1 sulfur and 4 fluorines. Since there's only one of the first kind of atom, we don't have to say mono, we can just say sulfur. And then those 4 fluorines would be tetrafluoride. So sulfur tetrafluoride is the picture that I'm looking for. that is actually a really nice picture. And you can see sort of an empty space sitting right here. That is where that lone pair on sulfur is. That's pushing all of the other electron groups out of the way. Now, a lot of these places, we should actually be able to get a three-dimensional model. Oh, you know what? I'm going to do something else. Let's see if I can do the... I have this fancy program. This is a paid program, but no big deal. Like, we can use it so you can see what's going on. So if I... Now let's see if I think I should be able to convert this into a three-dimensional structure here. Maybe not. Give me just a second. Ah, I just got this new version of ChemDraw and I can't find anything. So imagine the same things that you would expect from a new version of Microsoft Office. I don't understand. Maybe I can pick up and drop. No. No. Yes. That's what I wanted. Oops. There. I should be able to rotate this. And that is not a correct structure. Okay, I'm abandoning ship on this. That's so lame. Spend lots of money for a program. There we go. We should be able to, yeah, that's what I'm talking about. So ChemTube 3D is an awesome website because I can actually click and move this thing around in 3 dimensions. So remember I said sulfur's yellow, halogens are green. This has a really interesting shape, okay? Now you have to super use your imagination and imagine that this atom and this atom and this atom are sort of forming a lever point in the middle, and then there's a plank here and a plank here. And if you look at it careful enough, or if you like cross your eyes, this looks a lot like a seesaw that you play on when you were a little kid. Like that's the plank that one kid sits on here. That's the plank that another kid sits on there. So we actually call that shape the seesaw shape. Isn't that interesting? So there's actually two allowed names for this shape, seesaw, or anybody remember the other name that you gave to a seesaw when you were a little kid? What else could you call a seesaw? Tristan, you don't know? Have you ever heard the term teeter-totter before? A teeter-totter? Yeah. So some people call that shape around that sulfur teeter-totter. Anyway, the names get the shape names get really, really interesting and surprising and fun when you go beyond 4 electron groups. But if we just get up to being able to predict the shapes for things with up to 4 electron groups, that's good enough for our class. That's good enough. Checking to see. I'm still working on grading you guys' exam 1s. They'll be done in a few days. And we'll talk about them probably next Tuesday. Like do the exam recap. I think we're supposed to be starting chapter 5 today. Yep, supposed to be starting chapter 5. That's totally okay because chapter 5 we get 2 weeks for, and as long as you're watching videos, there's no reason that that can't be a little bit shorter. So if we have to spend the rest of this week talking about chapter 4 stuff, there's a lot to unpack in that chapter. So that's fine. It's totally fine. We've talked about shape, and we're at 1 hour and 10 minutes. We probably don't have enough time to talk about polarity today. So I'm gonna shove that until Thursday's class. Do you guys have any other questions? Is something uncomfortable about those shapes? So that's an important concept because thinking 3-dimensionally about those central atoms and knowing what shapes they have is going to be super important when we start talking about whether molecules are polar or non-polar. And then also in chapter 8, talking about something called intermolecular forces, which we'll get to when we get to. Excuse me. Okay, if there aren't any more questions, I don't have a 15 or 20-minute topic left to do tonight. So that's going to have to be where we're done for the night. Jennifer, do you have study tonight?
I do. I was also hoping you could stay on for a couple minutes with me after where we stopped recording.
Yeah, absolutely. So I'll stick around, and if you guys want to bust loose so Jennifer and I can chat for a minute, then I'm sure that she'll be over in her office hours in just a few.
Yep. Thanks.
Sounds great.